Welcome to Calculus 3. This is section 13.5 in your textbook, in the ApexCalculus textbook. This is on surface area. So when we have a multivariable function and we have a surface, we're often interested in finding the area of the surface, as we've shown here in the rectangular region here. We have the area that we'd like to find. We have the tangent vector u and v describing this area. We can project this down onto the xy plane as a little change in x and a little change in y. Ideally, we would be able to find, in terms, if f is a function of x and y, then determining the surface area of the function f of xy, we would use the projection onto the xy plane. And in fact, this is what we do. So our definition of surface area, given that we have some surface, we need continuous derivatives. So here, our surface area. Your textbook just leaves it as S, but we'll call it SA. So let Z be our function f of xy, where we have continuous partial derivatives, f sub x and f sub y, that are continuous. This allows us to take nice and pretty partials, and they're continuous over the closed and bounded region R. These are just a setup for our definition. Region R. So then the surface area is defined to be the double integral over the region of ds, which we can then define as the square root of 1 plus the partial derivative in the x direction plus the partial derivative in the y direction squared dA. And let's make a little note to this ourselves, that this looks very similar to the arc length formula. So in Calc 1 or Calc 2, arc length looked like we had the square root of 1 plus f prime of x dx over some region a to b. So if we think about in Calc 1, if we have only one dimension, we're in a similar position as finding the surface area, except for we're finding the surface area only over a single dimension. So this has some analogies to arc length. It's not exactly identical, but it's close. So let's do an example. Let's first set up an integral. So on the left here, we have an image of the function f of xy equals 1 over x squared plus y squared plus 1. And let's suppose we're looking at the circle defined by x squared plus y squared equals 1. So here we have a circle with radius 3, and we're looking for the surface area of this function inside this circle, so kind of the top of the hat. So we need to first take our function and take its partial derivatives. So f sub x, when we think about this, taking our partials, we're dealing with the circle, and we're dealing with a function that has x squared plus y squared. So a good transition to this would be to use polar coordinates. So polar coordinates are often helpful when we're dealing with circles as our regions. So if we translate to this polar coordinates, f of r theta looks like 1 over r squared plus 1. And our region then is bounded as r goes from 0 to 3, and theta goes from 0 to 2 pi. So instead of dealing with x and y as our boundary, we're now dealing with polar coordinates. So f sub r is negative 2r over r squared plus 1, quantity squared. F sub theta equals 0. So our double integral is 0 to 2 pi, 0 to 3, the square root of 1 plus f sub r, quantity squared, so negative 2r over r squared plus 1, quantity squared, that entire piece squared, plus f sub theta, which is 0, squared. And then our Jacobian, because we made the transformation to polar coordinates. And this is our setup for our integral. Notice that this looks a little bit tricky to solve, and often with surface integrals, we use technology to solve it. So let's look at a function that's a little bit easier to solve by hand. So let's find the surface area of f of xy equals 3x minus 7y plus 2 over the rectangle defined with opposite corners x equals, or excuse me, points -1, 0 and 1, 3. So we know that our region is defined as a rectangle. So x goes from -1 to 1 and y goes from 0 to 3. So that's our region here. And if we have our surface, f sub x equals 3, f sub y equals -7. So this is a nice integral to set up. 0 to 3, -1 to 1, square root of 1 plus fx squared plus fy squared dy dx in the order that we've, dx dy in the order that we've set up our integral. So we get 0 to 3, -1 to 1 of the square root of 59 dx dy. So we get 0 to 3, 2 square root of 59 when we evaluate the inner integral, dy, which gives us 6 square root of 59 as the surface area for this function on this region. So the next video will demonstrate 2 more examples of finding surface areas. So if you have any questions, as always, feel free to email me.